Okay, so you've memorized the reactions for this chapter, you're trying to apply them to problems. You look at a problem like this, and you want to identify three things. What are you adding, where are you adding it, and how is it going to be added? So here you would look at this recipe where you have an alkene, and then you have mercuric acetate with water in the first step, and then in the second step, sodium borohydride, and you'd say, oh, that's definitely oxymercuration-demercuration, because you have learned it already. There's no way around that. And so when you recognize that it's oxymercuration-demercuration, you know you're going to be adding an H and an OH. It's Markovnikov addition, which means that the hydrogen will go to the less substituted carbon. And there's no rearrangement in this case. No rearrangement. So thank goodness we don't have to worry about that. And then how is it going to add? This is, again, you'll just have to worry about whether you have a chiral center or not. If you form a chiral center, then you will have a racemic mixture. That's a 50-50 mixture of the two enantiomers. So 50% R, 50% S. And that's just because you'll have an intermediate, because these alkenes are flat. And so in this particular reaction, it can happen with equal likelihood on either side. And so that's why you'd have 50% of each side reacting. And if you don't have chiral center, then you don't have to do anything special. Okay. So now that you sort of worked that out, we can apply it to this molecule. And so we'll take this, and because we do not have rearrangement, we know that the two things we're adding will definitely always be on the two carbons in the double bond. So it's just a question of which one would they form on. So the one on the top is primary, the one on the bottom is secondary. And because this is Markovnikov addition, the hydrogen will go to the less substituted carbon. So the hydrogen will go to the carbon on top in this case, and you'll use the pi electrons to stick that hydrogen there, so you won't still have that pi bond. And then, because there's no rearrangement, the OH will add to this other position, this secondary position. Make sure the bond goes to the oxygen. Hydrogen can only form one bond. It's going to be to the oxygen, so the oxygen has to be bonding to the carbon. So make sure that that bond to the carbon is not going to the hydrogen. It has to be going to the oxygen of the OH. And so that would be an acceptable structure, at least as far as the where goes, the what and the where. The last thing we have to think about in this case is a chiral center, and in this case we do have a chiral center. So it's the carbon that has the OH on it. That's bonded to 4 different groups. And one thing I'm going to do to help simplify the structure is I'm going to erase the hydrogen. It's still there, it's just being implied, rather than drawn in explicitly on this skeletal structure. And to draw the two enantiomers, in one of them you'll have a bond coming out at you to the OH, and in the other you'll have the bond to the OH going away. And so one of these is R, one of these is S. You don't have to label which is which, but you do have to draw the two enantiomers. And so those would be the two products you would get in the case of this reaction. All right, let's go through that same thought process, same with another oxymercuration-demercuration. So you'd look at this reaction. For example, you'd see an alkene. You'll see it mixed with mercuric acetate and water in the first step, sodium borohydride in the second step, and you'd say, oh, that is, thank goodness I spent all that time early memorizing the reactions long before the test, because I know now that is oxymercuration-demercuration, and it comes with this what, where, and how. So you can take the molecule they're giving you then, and there's no rearrangement in this reaction. The only reactions that have rearrangement in this chapter are hydrohalogenation and acid catalyzed hydration. So if there's no rearrangement, then you know that you're going to be adding things onto those two carbons that are in the double bond. And so you'll look at those, you'll classify those. There's the tertiary carbon on the left, secondary carbon on the right. This is Markov-Makov addition, so the hydrogen goes to the less substituted carbon, and you erase that pi bond. You use those electrons to get that hydrogen on there. And then the OH, the other thing, will go on the other position. There's no rearrangement, so we don't have to worry about that. And in this case, we don't have a chiral center, so we're done. And you could leave it like this if you wanted to. Ideally, though, especially as you continue to practice, you would be able to erase that hydrogen. It's still there, it's just being implied in the skeletal structure. And so that would be the product you would get for that reaction. So those are some examples of how you might predict the product for an oxymercuration-demercuration one-step synthesis where they give you all the reagents.